So this video is simply a tune-up of my wireless set 19. This 19 set has not really been touched since I initially put it back on the air. And this is an American wireless set 19, so I have an American Mark II procedure here to go through. I use the set in a non-traditional way. That is, I have a well-regulated power supply. I do not use the antenna tuner with the set. I have my own pi filter because I'm a little nervous about using a 19 set on the air with only one tuned circuit. So with the pi filter, it gives me more harmonic suppression. I don't use it really to match the antenna. The antenna is already matched to 50 ohms and it works perfectly right into 50 ohms. But with the tuner, I feel a little better that I'm not putting out harmonics. So that's what that's all about. Also, I don't really use the AM portion of the transceiver. I use it strictly on CW, and it works very well on CW with a regulated supply. So I'm breaking all the rules essentially, but it's still a 19 set, and it's a lot of fun to operate. So let's go through the alignment. First, a little bit of history on the set. I'm no expert on foreign sets and British sets like this one, but I want to take you into it a little bit, explain some of the circuits before we get into the alignment. So let's talk a little bit about the wireless set 19. The set itself is a complete military transceiver for use in armored vehicles. The power supply is fairly conventional, uses 500 volts for the final. 275 volts for most of the circuits, and it's a 12-volt relay and filament system. The B set is a super regenerative transceiver. Basically, it's a transmitter receiver in effect. They use an ultra-audion oscillator both as a modulated oscillator in transmit service and as a quenched super regenerative receiver in receiver service. And this circuit was fairly popular in the 30s for different types of short-range transceivers. However, it's got some limitations. When you're trying to use the oscillator as both a receiver and a transmitter, it usually means that you can't use an RF amplifier up front to isolate the receiver from the antenna. Consequently, the receiver puts out a lot of noise that can interfere with other nearby receivers. And of course, the B set, which we're talking about here, was meant for short-range vehicle-to-vehicle communications. So the very thing it was designed for, it turns out a super generator without an RF stage is very poor at. So they were essentially jamming each other at close range. Perhaps two of the sets could operate very nicely, but once you added 3 or 4 or 5 different vehicles trying to communicate, basically the B sets would interfere with each other and it would be just a complete mess. So not a very successful circuit. The B circuit, of course, wouldn't be legal today on the ham bands today or any commercial bands. So getting the B set operational, it's a nice exercise, but it's not really a useful circuit on the air. So the A set is really what we're interested in, and the A set is really a single conversion super heterodyne transceiver. It's one of the first devices that shared all of the oscillators between the receiver and the transmitter, and it's an interesting circuit. So if we look at the circuit from a block diagram standpoint, it's a little bit hard to take it all in at once. You know, you've got things that you recognize like mixers and IF amplifiers and power amplifiers and so on. But it's a little difficult to make sense out of this block diagram. So I thought I would simplify it down into something that you might recognize, a little more modern type of schematic diagram. As you can see, in receive mode, we're going to use 7.12 megahertz or 7120 kilohertz as our experimental frequency. Comes in through the PA filter, and the receiver is coupled right to that filter with no relay. Hey, that's been seen in some modern QRP rigs. Just take lightly coupled right off the PA filter, bring it into an RF amp, and then we mix it. We mix it with high side injection. So for 7120, we put in 7166, and we get a 465 kilohertz intermediate frequency, which we amplify, send to a simple detector where we have a BFO operating 800 hertz higher, and voila, out comes the audio. So it's a very simple single conversion super heterodyne receiver, and that should be very familiar to everybody. Now let's talk about the transmitter. In transmit service, that same BFO that we had, we put into a fixed mode, so it's operating very close to 465 kilohertz exactly. We send that into another mixer where we inject that same high side 7166 kilohertz, and you subtract 465 from 7166, and bingo, you get 7120 out, which we amplify and key and send out the filter. Thus we have a single conversion super heterodyne transceiver based on 2 oscillators and 2 mixers. This topology looks familiar to you because a lot of the modern QRP rigs, at least the QRP rigs of the 80s and 90s, which use chips like the NE and the SE602, the 1496, and many other Gilbert cell type mixers, and passive mixers, use this topology. It's a very common topology, a single conversion transceiver using 2 common oscillators. It's very cleverly done in the wireless Set 19, and now you know where all of this came from. A lot of the circuits that we use today in solid-state QRP came directly from the wireless Set 19. I was interested in using the HF part of the radio, and I really wasn't that interested in AM with it or the UHF transceiver. So I just wanted to get it basically receiving and transmitting on HF. I did not go as far as to collect the antenna tuning unit or the appropriate DC power supplies. So I made my own power supply, and after looking in there and seeing all of those capacitors, I decided that I would just do a blind recap. What's a blind recap? That's where you basically take every paper capacitor in a radio and you replace them all. And I proceeded to go through the radio and changed all of them out. That's before attempting to light anything up or apply power or do anything. I just blindly recapped the whole thing. I thought that would be a good starting point for the radio. So eventually I was able to get the radio to function, and it actually turned out to be a very fine CW rig. I have a video on YouTube showing it operating in the CW mode, and it does very well on CW. Of course, I have a pretty good power supply. I would say maybe 10 years I used the radio successfully. There came a day, probably about 5 years ago, where there was no more drive. The receiver still worked, but no more drive to the final. And I might mention the final is a 807. One interesting thing about the design of this radio is that it uses commercial off-the-shelf parts, COTS parts, non-militarized parts. And they had some pretty strict rules with the manufacturer that any one piece, any one stamping, any one dial or mechanism had to be less than a pound in cost. So this radio really represents the first COTS attempt, building a radio from commercial TV and radio parts mostly, with a few low-cost stampings and metal items, and you end up with a fairly low-cost, easy-to-reproduce radio. So this particular radio, let's talk about the pedigree of this radio. This radio is actually U.S. It was manufactured in New Jersey by the RCA company, and I will tell you, during the darkest days of World War II, a lot of technology came from Britain over to the United States and to Canada. And the radio was first brought to Northern Electronics in Canada, and they began to produce them. A team from Northern came down to RCA and brought them up to speed on how to source the parts and begin manufacture of the set. This represents one of the early American attempts to build the wireless Set 19. It's from 1942, and it's a low serial number 7030. So this is one of the early United States manufactured wireless Set 19s. Everything is in English. There's no Cyrillic Russian on this radio. This is built as an American transceiver. So these radios were destined to be put into Lend-Lease equipment that would be shipped over to Great Britain by the convoys, and this would allow them to have a familiar set in some of the early armor, such as the General Lee tank and the Shermans. Later on, equipment will be put in there with FM gear for D-Day and so on. But these radios were used in conventional armor, and they were manufactured along with the tanks and the armored vehicles in the USA. Now, how many of them actually made it overseas in the armor? I don't know. This set possibly was never deployed. Even though it was dirty and missing its case, who knows, maybe it was just used as a practice radio. So, having lost drive, we need to find out why the set is not functioning. So I'm kind of glad I went through the exercise with the wireless Set 19, because I found something kind of silly. And I found something that was a legitimate problem. Here's the power supply over here. What I found was I had an intermittent wire on the medium voltage supply, which is around 275 volts. And it was good that I kind of ripped into everything to find that wire. But the real problem turned out to be, of all things, the key jack, or the key plug, I'm sorry. This is the key plug. And this is the key. Basically, I had rewired the key to key up the TCS transmitter, which also uses the very small PL68 style, which is a 3-circuit telephone type jack, and it's thinner than a regular 1/4-inch phone plug. And I had wired it for tip and sleeve. Okay, but and that's what the TCS wants. But the wireless Set 19 wants tip and ring. Sleeve is not actually used. It's just used to open the jack up to mute the set. So, nothing but a miswire on the key. When you put the key in, it mutes the receiver, and when you close the key, it keys the screen and plate of the driver. I'm sorry, the screen and plate of the heterodyne oscillator, and the screen of the final. So it's screen grid keying. So it was just a miswire on the key. There was nothing actually wrong with the drive on the set. And the way I was able to troubleshoot it is when I put it into the phone or the receive transmit position, I had drive. So I knew it wasn't broken inside. I knew it had to be something pretty simple, either a bad switch contact or something in the key line was open. But good to have this set back on the air, because it's a lot of fun to use. I'm going to try to align the wireless Set 19 Mark II, and First of all, I want to show you something that's a little different on this radio. As you can see, the 6K8 glass in this particular radio in these two spots have been swapped over to metal tubes. This is sometimes done because you can't get a hold of the glass tubes, but in my case I did it because I wanted more stability in the radio, especially with the 6K8. Okay, so here are the 6K8s, and you might notice that their positioning is such that we have the master oscillator and the frequency changer tubes as 6K8s each side of the RF amplifier, the 6K7. I just want to mention that I've converted those to metal tubes. This is quite a popular thing to do both on the wireless Set 19 and the R1155. There's a lot of controversy over switching to metal tubes, and it can be especially dangerous because pin 1 of these tubes is not used on the glass tube, but on the metal tube it's what connects it to the built-in shield on the metal tubes. So if the manufacturer happens to be using that pin 1 terminal as just a terminal and as a handy tying point, and you plug in one of these metal tubes, you're going to have a big short, a big explosion. So just be careful of pin 1 when you do a metal tube conversion like this. That said, it is notably more stable using these tubes than the original glass tubes with the shields. The other note is notice how they put the oscillators in one section off to the side. As with two oscillators producing a frequency, either one of them can cause drift. Hopefully they both drift the same amount and cancel each other. Isn't that an interesting idea with a super heterodyne style transceiver? Okay, so now we get out our instructions and we go to the chapter that starts the alignment procedure. And what I like to do is blow it up and make notes and make sure you're working on the right set. This is the Mark II, not the Mark I. One more thing about doing alignment on any radio like this. And you'll see me fooling around tuning trimmers and transformers with the set on. We have high voltage here, and you know the high voltage we're talking about is 500 volts on the plate of the final amplifier, the 807, and 275 volts for most of the other circuits. So these are lethal level DC voltages. So let's just keep in mind that we have high voltages, and before we get too wild inside a set like this, just remember these things can be lethal if you get across the wrong things and cannot release. So we have to build an injection circuit to put the signal right into the tube. We're going to lift up the grid cap, take it right off, and we're going to install our own grid cap. Okay, and we have this, it's a 500K resistor, but you could use a 470 just as well. And this has got to go to ground, so you got to figure out how to, some place where you can clip this onto ground. I got an alligator clip, so I'll clip it onto something. And then we're going to put the generator between this and ground, and that's going to inject signal right into the mixer tube, or into the converter tube. We're bypassing the RF amplifier. So the first thing we're doing is determining how good the IF is, so we're injecting the IF frequency of 465 kilohertz. I found that the radio has good sensitivity, and it's peaking around 467. And according to the instructions, if it's between 462.5 and 467.5, that's within limits of the tuning. So I am not going to touch the IF transformers. There's always a chance that something could crack or break inside them, and since we have good sensitivity and we're within spec, I'm not going to touch the IF. I'm using a 400 cycle, 30% modulated signal at a very low level. so as to be able to work with the IF. So next we'll check to see if the BFO is going to work over that range. So we need to kill the modulation on the generator. Go to CW. And then we need to go to CW on the radio. And good enough. I think that's fine. As a CW signal, I think that's acceptable. Okay, as a final check, what we need to do is see if we can net the frequency. So we go to RT. From the CW position, we go to the radio telephone position, and we're going to push the net switch. And we are going for 0 beat. So we push the net switch, and then tune the oscillator. So the BFO is centered at 466,829, and when we go back to CW, we hear a nice, pleasant CW tone. That's properly tuned. Where are we in the process? So far we have verified the IF, we have verified that the BFO is roughly centered on the IF, and we verified that our netting switch is giving us a 0 beat. So this being a real transceiver, and a transceiver being a transmitter and receiver that are sharing the same oscillator, basically. That's the basic definition. They may indeed be sharing more circuits, but at least they are sharing an oscillator. In this set, being a single conversion super heterodyne transceiver, the oscillators are shared between the units, and so therefore it meets the criteria of being a true transceiver, not a transmitter receiver. Now, in the next part of the tune-up, we're going to be concentrating on the dial. As you can see, it's an interesting dial in that they have the low frequency band over here and the high frequency band over here. It's a 2-band radio. So you've got the low band and the high band. So what you want to do is, if you're on 40 meters here at 7 megahertz, you'd like that to be accurate. And when you're at 3.5 and 80 meters, you'd like that to be accurate. But the way the tune-up goes is you start in the high band and you set the dial for 8 megahertz. And get that set point with your generator. Then you go back down to 4.5 and check to see that the dial is within a couple of divisions, okay, of being at 4.5. So you'll do that for both bands. And there's a pair of coils underneath on ceramic, and those coils are what determine, along with some fixed caps and these capacitors on top, how that dial is going to end up. Now, as the sets age, you find that instead of going from 4.5 up to 8, instead it goes 4.5 to 9 or 4.5 to 7.5, and you don't get the dial divisions to line up. Next, we're going to be injecting at the RF amplifier V1A, which is the middle tube. So we've moved our injection system for the generator. I have to take the bottom plate off. By the way, this is a homemade bottom cover. I made out of a piece of old sheet metal, and I marked the capacitors. It's handy to have those marked and some holes so you can align through the metal chassis. It gives you better alignment. And I've also drilled some holes that allow some ventilation through the chassis in some key spots. Now we're going to tune up the A-set sender, and we're looking for maximum drive on the meter. So when we hit transmit, you can see the meter, it's already over 5 here, but it says to go to the high band and tune to 6 megahertz. I actually like to tune it up on 7 megahertz because we're going to be using it mostly on 40 meters. So I've got the dial set to 7 megahertz, and we're in the high band position. Now you have to tune the PA tank as well with this control to maximize the drive and the output. Actually, to maximize the output. The drive won't vary, but the output meter will vary as you tune the tank. So watch the meter. As you can see, as I'm tuning the tank, I'm able to get out. I'm already getting out almost 20 watts. So you can tell this set is well tuned up. But what they want you to do is they want you to touch up the 2 tremors that are on top here, C10B and C10C, and this is the sender drive and the sender RF. So those are the 2 that we'll be touching. So now we're going to do low band, so we need to switch bands. This is upside down, of course. Now you'll notice that I'm in transmit because I put the key in, and when you put the key in, it actuates the relay, and when you key, you're just keying voltage on the final, and it's really elegant because you don't have all that clinking and clunking that you have with typical sets that key everything with relays as you key. So I'm going to set the dial roughly at 3.5. Let's see what we got here. Okay, we're getting good output. Yeah. Okay, about 16 watts out, and we have pretty good drive. It's right at 5, a little over 5. So let's try those 2 trimmers. First this one over here. Ah, that one is working. Okay, I can see that one changing. Try to go back to that other one again and see what the issue is. Not seeing that change much. So I'm not seeing much on C10E, but seeing C10F. So about 16 watts. So we got plenty of drive and plenty of output. Now you might be asking, what's C34A all about? And what that's all about is that's your AM adjust. So you go to RT and you adjust that, and you can see that affects the AM. So just peak that. Here's where the stupid yank doesn't know what he's doing comments start. I was not able to achieve what I would consider to be good tracking with the dial, especially band to band. And I tried a capacitor across the low frequency coil to try to bring it into alignment, and I could indeed get 80 meters and 40 meters to line up quite well, but again the dial would become misaligned end to end. So the book tells you to fool around with the coil. Well, there's no slug in the coil like you would have with a normal radio, where you would have a variable capacitor and a coil that you work against each other to spread out the band or to tighten it up to make it match the dial. So I decided that maybe I would try something a little bit radical, and that is to put a tunable slug in the end of the coil. So I've taken a slug-tuned coil apart and just taken the tunable part off the top of the powdered iron part off the top of the coil form, and I've jammed it inside the coil and then epoxied it in place, and I have a keeper nut here. And the actual ferrite is just barely into the coil, but that's enough to bring it down and give me that 2-factor adjustment that I need to do this right. We're going to try this trick and see if it's stable, and if not, then I'll rip it out. But I've now made a tunable coil out of a fixed coil. Okay, it's now doing what I want. I have the dial at 3.5 and we're at 3.3, so it definitely made the frequency go down. Okay, we've accomplished it. 3.5 megahertz is where the 3.5 megahertz dial is. And we have plenty of play in the coil. The slug is almost totally out. And again, this represents around 5 to 7 picofarads that I had to put on the coil to bring it into resonance. But it gives me adjustability instead of fooling around with fixed caps. And of course the fixed caps don't go away at the other end of the band. So this gives you that 2-factor effect when you're trying to spread out your dial. Now once we're done, I will put that locking nut down and that coil should stay. So one more super important note, and that is to check the oscillator with your counter that it is the IF frequency above the frequency you think you're tuned to. So if you're tuning around 7 megahertz, you want to see something like this on the local oscillator. If you tune the local oscillator on the low side, you'll have an embarrassing out-of-band signal. So you need to probe your counter right into the oscillator compartment, close enough that it can pick up and read, and assure yourself that you're on the high side. So pretty successful. I've certainly got it working pretty well on 40 and on 80 meters CW, where I mostly want to use it. You have to be very careful with the trimmers, because it's easy, even at this late stage in the alignment, to be on the wrong side and consequently out of the band. So just make sure you're using your counter a lot to validate that you've got the right side injection. It is fairly easy to get from one side to the other because it's a single conversion IF, and tuning in megahertz is not very difficult with these trimmers. As you know, the set tunes very quickly and the trimmers tune quickly as well. So you might be asking, what does the Wireless Set 19 represent in terms of equipment in a typical armored vehicle? Well, if you take the American equivalent of how much equipment it would take to replace the Wireless Set 19 in a tank, let's look at what the Americans entered the war with the Lee Grant style tanks that were the first Lend-Lease tanks that were sent over into the North African theater. So first you needed an HF receiver, and here we have the BC652. Then we have the BC653 main tank transmitter. Okay, so this covers from 2 to 6 megahertz, and the wireless set 19 actually goes all the way to 8 megahertz. So it's already giving you more coverage than this American set. Here we have the BC322 Super Regen transceiver. Essentially that circuit inside the wireless 19 as well. But beyond all this, the 19 set also includes the tank's intercom services. In the American tank, that would be the BC322 or equivalent. So you really have a system that is easier to use and much, much smaller.